All right, let's talk about a kind of superpower. We're going to dive into the science of seeing the invisible, how thermal imaging lets us spot huge failures in buildings and machines way before they ever actually happen.
I mean, just think about that for a second. What if your most important systems, the electrical panels, the roof over your head, your heavy machinery, could actually warn you that something's wrong before you smell smoke or see a water stain? Well, they can. They are constantly speaking a language, but it's a language of heat.
Okay, let's just jump right in. On the left, you've got an electrical panel, just what you see with your own eyes. Everything looks totally fine, right? But now look at the right. This is what a thermal camera sees. That one glowing, bright yellow spot, that's a dangerously loose connection, screaming with heat. It's a fire, just waiting for its moment to happen, and it's completely invisible, until now. This, right here, is the superpower of thermal imaging.
But, and this is a big but, here's the catch. The camera is not a magic wand. It's a scientific instrument, and if you want to get the truth out of it, you absolutely have to understand the rules of the game.
Which brings us to the real heart of the matter for thermography. You've got to learn how to separate the real thermal signal, the important stuff, from all the other environmental noise that can completely fool the camera.
So here's probably the most important thing to get. The camera doesn't have some tiny little thermometer that it can point at things. Nope, what it actually does is measure all the radiant energy that hits its sensor. And that includes both the energy coming from the thing you're looking at and all the energy bouncing off it from everything else around it. And this combined kind of messy reading, that's what we call apparent temperature. It's really just the camera's best guess. The whole job of a professional thermographer is to be a detective, to scientifically filter out all that interference to find the true temperature that's hidden inside that number. I really like this slide because it breaks down this whole battle. The signal, that's our hero. That's what we want. The true energy coming from the object itself. But to get to it, we have to defeat the noise. And these are the villains of our story. You've got reflected energy bouncing off other objects, the sun heating things up, and even wind, which can literally blow your heat signal away.
So, how do we defeat these thermal illusions? Well, it all starts by mastering the biggest and, honestly, the most deceptive source of noise there is, reflection. And to do that, you have to understand the single most critical setting on any thermal camera, emissivity. All it is a measure of how good a surface is at broadcasting its own heat. It's just a score on a scale from 0 to 1.
This here illustrates it perfectly. High emissivity materials, like concrete or just plain old paint, they're like loudspeakers. They are fantastic at shouting out their true temperature. But low emissivity materials, like shiny metal, they're awful emitters. And because of physics, if you're a bad emitter, you have to be a great reflector. They basically act like thermal mirrors, showing you the temperature of their surroundings, not their own.
And this, of course, leads to a really practical problem. How on earth do you get an accurate temperature reading from a surface that's basically just a mirror for heat? Well, it's pretty clever. You fight a mirror with another mirror. This is a standard trick you can use in the field to measure what's called the reflected apparent temperature, or RAT. You just take a piece of aluminum foil, crumple it up and flatten it out, and put it near what you're trying to measure. Because the foil is an almost perfect reflector, its temperature reading is really just the temperature of the stuff around it. You measure that, punch that number into your camera settings, and boom, you've just scientifically canceled out the reflected noise. And trust me, this isn't just for fun. Get this wrong, and you might think a perfectly healthy motor is about to explode just because it's reflecting a hot pipe behind you. That's a super costly mistake that a little piece of foil can prevent.
All right, so we've taken care of reflection, but there are two other villains that can totally wreck an inspection. So let's move on to mastering time and power.
So the key to mastering time is this concept called thermal inertia. It sounds fancy, but it just means how stubborn a material is when it comes to changing temperature. Things with high thermal inertia, like water or concrete, are kind of like thermal batteries. They soak up heat really slowly, and they release it really slowly. Now this timeline shows you exactly why timing is everything for something like a roof inspection. During the day, the sun is just blasting the roof with energy. You can't see anything. But after sunset, the cooling race begins. The dry parts of the roof, with low inertia, cool off fast. But any trapped moisture under there, it acts like a high-inertia heat battery, holding onto that sun's energy for much, much longer. This creates a huge temperature difference, a maximum delta T, but only in a short window, maybe an hour or so after sunset. That is the only time you can get a clear signal to find a tiny leak before it destroys the whole roof.
Okay, now for power. The rule for any electrical or mechanical system is absolute. For your inspection to mean anything, that system has to be running at over 50% of its rated capacity. And the reason is just pure physics. The heat that tells you there's a problem is created by electrical current flowing through resistance. It's like friction. The more current you have flowing, the more heat you're going to generate. If there's no real load on the system, there's barely any current. No current means no detectable heat. A fault that is completely invisible at 10% load can be a raging fire hazard at 90%. You have to test things when they're actually working hard.
So, the takeaway here is that some conditions just make your data completely worthless. These are the absolute red flags. Wind over 15 miles an hour is literally blowing your evidence away. Direct sunlight is masking the real signal. A wet surface creates false cold spots from evaporation, and of course, not knowing the system's load. Any one of these, and your inspection is basically invalid.
Okay, so you've done it. You defeated the noise, you timed it perfectly, and you made sure the load was right. You have a good, clean, trustworthy thermal image. So let's get to the final step, turning that data into an actual decision.
This is where industry standards, like this one from the NFPA, are so powerful. They take all the guesswork out of it. As you can see here, a temperature difference, that delta T, of a few degrees over a similar component, just keep an eye on it. But once you hit 16 degrees or more, that is a critical priority. That means fix it now. It turns a heat map into a clear work order.
And professional reports add one more layer of intelligence, a confidence rating. A high confidence finding is definitive. It's confirmed. All the data lines up. But a medium rating is more of a heads up. It's saying the pattern looks like a problem, but it needs to be physically verified. This is how you deliver information that's not just a pretty picture, but is defensible and actionable.
Which really brings us to the most important point of all this. A thermal image is not the final answer. It is the beginning of an investigation. It's an incredibly powerful diagnostic tool, a critical piece of evidence in the science of keeping things from breaking. And so we end right back where we started. Your most valuable assets, they're constantly communicating their health to you in a language of heat. The only question left is, are you equipped to listen correctly?